Hello, my name is Walter Ellsworth, and welcome to my presentation of Lab 3 Magnetic Field of a Bar Magnet. The purpose of this lab was to gain a better understanding and visualization of the invisible magnetic field around a bar magnet, and then to use this relationship that we visualized to better understand the relationship between the distance and the magnetic field, and then to use the equations we know from Biot-Savart's law to make accurate predictions. Using those equations, I was able to find an n value of negative 2.7855, a dipole, magnetic dipole of 3.9865, a K value of 7.973 times 10 to the negative 7, and a net magnetic field of 5.882 times 10 to the negative 5 Teslas. The bar magnet acted as a model dipole in this lab, and the linearization model is down below that I used to find the values of K, N, and was shown before. And the magnetic field distance dependence equation shown below, and this was the Biot-Savart's law that I used to the right. The details of the experiment: the magnetometer sensor of my smartphone was first located, and then the table was set up in a line to compensate for the influence of Earth's magnetic field. And then the distances that produced the desired magnetic field readings were recorded for T values 20, 70, 120, 170, and 220. And then 3 recordings are made for each one. The initial conditions were that the phone and the I used PHYS magnetometer app, and that was installed onto my phone, and put I used a meter long stick that I taped down to my table, and I made that perpendicular with magnetic north. And then the bar magnet acted as the system. These are the measurements that I recorded using the previous procedure, as mentioned before, and the details of the experiment and the measurements. In order to measure the off-axis magnetic field, a second ruler was added in the opposite plane, as you can see to the right. Once the distance to produce the required observation is determined, the magnetometer sensor is moved the same distance in the perpendicular direction, and then the net magnetic field was calculated off of the x and y components. And as you can see below, a B net value of 5.8816 times 10 to the negative 5 Teslas was calculated. And the observations of this experiment were that when the magnetometer was far away from the magnet, it measured a near zero magnetic field in the x direction, and I said yes to this. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. I said no. And then because as you get closer, it increases the opposite. The position of the magnetometer has no effect on the measured x component of the magnetic field. It changes it's completely position dependent. As the magnetometer moves closer to the magnet, the measured x component increases. Yes, it's the opposite of 2. These are the calculations that I used to calculate the dipole, the B value, the total magnetic field, the value for K, and the value for N. This is the code that I used to make the model in Python. A lot of this is all determining constants, equations that we know. These are to determine the arrows in the visualization. And then this is the this is the model, the computational model. And possible errors were that the model B field was 3.78 times 10 to the negative 5 Teslas, and this inconsistency could have been done to personal errors and the fact that I was using a smartphone app and a ruler and a meter stick aligned with magnetic north, not very accurate. And what if I hadn't orientated my experiment to compensate for magnetic north? There would have been interference measured in the x direction specifically. And if I were to stick 2 identical magnets together end to end and run the experiment again, how would I expect them to differ? I would expect it to increase and potentially double if the magnets are both the same size. All right. Thank you very much.